Hello everyone, I'm Khushwant from ETAS Script. Thank you ESSS 2022 for this opportunity. I will be presenting on challenges and opportunities for automotive industry in ever-evolving cybersecurity space. So, quick look at the agenda. We'll cover the advent of software-defined vehicle, cybersecurity in the context of software-defined vehicle, challenges, of course, that's what we want to know, emerging technologies, and some long-term opportunities for future. So, software-defined vehicle per se is a paradigm shift the way we have seen the vehicle development, vehicle software development for that matter. The term itself implies that there will be software which will drive vehicle functionalities. So, the idea is that the vehicle on field will be continuously updated with various software features. The features will be kept up to date to ensure that the vehicle remains relevant even till the end of its life. A lot of factors are driving this new mobility concept, like autonomous driving, for example, is the big one. Connectivity, mobility as a service, shared services, big data, electrification, that's a big one. After sales services, all of these factors are sort of pushing the limits of the existing software development cycles, and it's increasingly becoming clear that there is no way that the existing v cycle development can really deliver a vehicle which can be kept relevant for a long time in field. A small example is we look at our mobile phones, right? They have we buy, let's say, on a date X, and then after a few months there is an update, then there is another update, and then the applications are updated. All of these updates ensure that the phone remains relevant for quite some time, right? At least year and a half or two is the typical life cycle. But vehicles, we cannot be changing in 2 years. It will be 8, 10, 15 years of life. Okay. So now when we look at this life, the individual functionalities on various ECUs should also be kept relevant. More importantly, from safety and security perspective. What do I mean by that? So the original idea of software in vehicle electronic control units came from efficiency requirements and safety requirements, like efficiency in terms of emission norms. Emission norms became stringent, more and more electronics started to be pushed into the vehicles. The efficiency definitely came, safety also came, but the problem was that this efficiency and the application software or the firmware were almost hard coded, and they could not be updated after the production. So you buy it and you stay where you are. But then came some features like convenience features or infotainment, also the new age features from electrification or ADAS functionalities. Now, these functionalities, the user need the latest experience. And if the user needs the latest experience, it implies that the software, there has to be a possibility to define the features of those particular devices or the controllers through a software update. So to ensure that the feature, the device remains relevant for some time. Now, so we have been doing feature-defined vehicle, or let's say software-defined feature, for quite some time. As I mentioned, infotainment is a good example. But it is not enough, because come ADAS, come autonomous driving, most of the data that is going to be acquired on the field is also going to be used as a test data for future, create a new version of the software, and push a better and efficient software into the vehicle. Now, that's the trick here. So if you want to get the field data of the entire fleet and create test cases for future, and then push a better software into the vehicle, this will determine that the features are up to date for a long, long time. Plus, all of this acquisition of data and pushing the data into the vehicle through firmware updates will need the security also to be relevant and up to date, so that a safe and secure vehicle remains on field. This entire concept is taking us closer and closer to a software-defined vehicle, in which almost all of the ECUs that the vehicle has will be one, updated from time to time for efficiency, for better functionality, for safety, for security patches, and it will ensure that the software as such will be decoupled from the hardware. So hardware more and more is going to be commoditized, and software is what will define the vehicle features, vehicle functionalities. So what does that mean? There is a lot of benefit that the OEMs will derive from this. Couple of those that I recall are manufacturing costs will be far lower than what we think for more or less all the parts. After sales revenue, you can determine a functionality which can be sold after the vehicle is already rolled out into the field. Yeah, so that's a good one. Maintenance, predictive maintenance, of course, you would want your vehicle to be maintained from time to time and directly by the OEM through the software functionality. So that's a good one. This will improve brand loyalty, and vehicle value will increase in field because at resale, when you have a vehicle which is having up-to-date features, most of the features up to date, apart from hardware which is not relevant or which is still relevant but not obsolete, but features are up to date and supporting most advanced use cases. That's fine. You will get a better value for your vehicle. And safety, right? The safety requirements will be always on a high. Now, when we are looking at delivering a software-defined vehicle, it's a very nice way, the buzzword of these days, but it's kind of complex. I've tried to simplify it a little bit for a common understanding. So a vehicle typically will have some sensors and actuators. The upper layer would be some embedded control units, ECUs, which will determine the behavior and response of the sensors and actuators. Over that is the entire software stack, right? This is where the personalization, this is where the feature enhancement, this is where the OEM value and the tier 1 value will come in. There will be some connectivity software which will support the entire vehicle architecture in connecting to the backend and delivering functions, features, functionalities. There will be some edge compute devices which will help in ensuring the efficiency, and whatever performance requirements are there, they can be taken care of. Now, on the back end, there will be multiple cloud architectures with which the vehicle is going to interact with. One of them definitely is the OEM cloud, followed by some third-party clouds like third-party payments, your any insurance agencies or any other third party that is relying on the OEM cloud to deliver services. And then there will be a development cloud also, right? So there will be some sort of a digital twin on which of the vehicle of the vehicle which is in field. There will be a digital twin, for example. On that digital twin framework, you would want to experiment as much as possible. You may want to run all the test cases, ensure that it is working fine. Then you do the field validation on actual vehicles, and then push all of those functionalities, features on this vehicle, right? Then there will be some other platform services, core services. There will be different portals. There will be some domain specific services which also will be a contribution directly from the OEMs or their suppliers for domain specific services. And this entire framework is what will determine the software defined vehicle. And this is by far a complex journey as compared to the original concept of vehicle start of production based on a V cycle development. Delivering a software defined vehicle is going to enable a lot of functionalities, but it will come with a lot of vulnerabilities also. And security per se is a key enabler to ensure that the connected software defined vehicle is relevant, is secure, and ensure that there are no malfunctions, there are no external misuse, abuses, breaches on the vehicle, so that the vehicle remains relevant and safe for the users. So, context of cybersecurity. So, when we look at software-defined vehicle, there are three main principles that we are looking at. One is the existing defense in depth approach, which we have been promoting, I think, from 2015-16 in India, and before that in the rest of the world. Making use of the defense in depth to deliver a secure ecosystem for the software-defined vehicle. This is principle number one. Second principle is the security should be from a design perspective. So designing a security and ensuring that the security is designed, the development methodology is changed in line with what the software-defined vehicle expects. So that's the dev part of the security development. And third is the managing part, which is the ops part of the security. This is after production, the vehicle is in field, and then how you ensure that the security is most up to date. So we are sort of alluding towards the DevOps principles, right? To deliver and ensure that the vehicle remains secure in field. Defense in depth. Why defense in depth? It's clear, right? It's no brainer. No single mechanism can protect against all threats. So you need to ensure that there are multiple layers of defense so that the impact of one, it makes difficult for the attacker to reach the real asset. That's one. Second is, even if in case of successful attacks, the impact can be minimized to the extent possible, right? That's more or less the principle. So these are the three main building blocks. There is an IT enterprise network. There is the vehicle network architecture, has all the four layers, from the ECUs to the external connectivity, and then the plant infrastructure. Yeah. What we mean by defense in depth, just a quick recap. So the individual ECUs need to be secure. The in-vehicle communication need to be secure. There should be some functional partitioning that can ensure that secure and insecure, safe and unsafe networks are isolated in a way that in case of a breach, the impact is minimized. And the external communication security. So this is first part, the vehicle and the vehicle external connectivity is secured. This is first part of defense in depth. Second part is the all of the security functionalities that will be implemented on the vehicle will be dependent on crypto credentials, which are injected in the production plants. So obviously the source of security should be secured first, which implies that the production facility should have proper mechanisms, checks and balances, production key servers to ensure that all the crypto primitives are fetched from the backend and injected into the vehicle. And the confidentiality, integrity, and authenticity of all of these credentials should be guaranteed. The third piece of the defense in depth is obviously the IT infrastructure. This is very well established system. The most of the IT systems, security management systems, ISMS, are capable to do this. There is a long history and quite mature way of handling IT enterprise security, and that should be leveraged on so that all the backend, be it OEM cloud or a third party cloud or a cloud service offered by a third party vendor supplier, all of these need to be adhering to the principles of enterprise IT security. So that's about defense in depth. Now, security by design implies that the V cycle that we were looking at, where a feature or a requirement used to be defined at the analysis stage, and then by the time it is validated and accepted, the relevance of most of the features have been relevant, but some of the features would have become vulnerable already because the vulnerabilities for those implementations were discovered in this duration, in this entire duration. So what happens with the software-defined vehicle is, software-defined vehicle is actually moving towards or alluding towards DevOps implementation because of the speed and efficiency and the flexibility that DevOps offer in terms of developing and ensuring that the vehicle is relevant in the field. So continuous integration, continuous deployment, continuous testing, these are more or less the terminologies that will be used. It will be very agile. A user story is created, feature is implemented, build is created, tested, released in the field, and then deployed. And then you figure out if there is any bug that is discovered. You then do the same cycle again. In terms of security, the V cycle model, which was looking at all of these activities like ensuring security, risk analysis, or create or implementing security functionalities, pen testing your development, all of these were done in a systematic way, but it was a very longer cycle. Now it will be sort of mimicking the CI/CD pipeline. Okay, so plan, code, build, test. This will be taken care of. The left half of the V cycle will be addressed through this, and the validation also will be pushed towards the test part of DevOps. And then comes the monitoring of the vehicle security. So the vehicle, when it was after ensuring that the security by design is implemented, vehicle is launched into the market, and the vehicles are on field. The vehicle security needs to be monitored from time to time, and that's where intrusion detection system or incident response as a service, threat intelligence, vulnerability management, vulnerability scanning on a digital twin, these kind of activities will become important. And this is the operations part. This is where you will monitor, so deploy, operate the functionalities, and continuously monitor. If there are any bugs, any issues found, then you again go back to the dev cycle. And whatever is the discovery of the dev cycle, to address the gaps that are identified, the vulnerabilities that are to be patched through security patches, can be pushed via a FOTA. So FOTA is a promising technology. As long as we ensure that the FOTA themselves are safe and secure, the vehicle safety and security can be guaranteed, because you will always keep the security of the vehicle relevant in the field. But all of this theory is very nice. However, implementing this security in SDV terms is not very easy. More importantly, when we look at this trilogy of challenges that we see, the regulations, limitations, and disruptions. Regulations, UNR 155 and alike, several of them have come up. GDPR, it's very important, because the software defined vehicle is getting so much information from the user, from the vehicle, from everything that is possible, and pushing it to the backend. GDPR becomes more and more relevant. Yeah. Limitations in terms of technologies of today, I'm not even talking about legacy technologies. Technologies of today are almost set to become obsolete when we look at the SDV implementation. Yeah. So there are several limitations with existing technologies, and an SDV cannot be realized based on such technologies. The third part is disruptions. There is a lot of technologies at the horizon under development, and they will soon disrupt the way we are developing the cybersecurity for SDV. I mean, SDV is still a far-fetched, even for the existing vehicle architectures. This is a big challenge. We start with the first topic, regulations. So several countries have done this catch up so far. And as we can see, even India is coming up with its own cybersecurity regulation for automotive. That's AIS 189, and AIS 190 is the SUMS equivalent, like R156 equivalent. Both of these regulations are more or less modeled on the WP29 UNR 155 and 156. So, as it is, we are looking at one of the most complete regulation to start with, and there is good amount of contribution coming in from SCRIP, from some of the leading OEMs in India, some of the suppliers of OEMs, and under the umbrella, under the guidance of ARAI, this regulation is being drafted. Yeah, and also the regulations, the most important factor is regulations are very holistic in nature. So there are four disciplines actually in this UNR 155 and AIS 189, which asks for implementing a cybersecurity management system as a first discipline. Second is ensuring that the security by design is the principle followed. So third principle is intrusion detection and monitoring to be implemented. And the final one is firmware over the air update, security and safety. So there is now a legal basis to ensure that any updates going onto the vehicle need to be tracked, and they should be secure. The security of those updates should be guaranteed. The safety should be guaranteed. So these four disciplines invite a lot of investment effort, and huge change in technology, people, processes, and implementing a governance structure across the organization to ensure that the security implementation done in one project is repeatable for all projects, and there will be a continuous improvement program also in place. So there is a lot that is set to change, and that's why it's one of the biggest challenges in implementing the SDV security. Second topic is limitations of existing technologies. As I mentioned, we are moving from current E&D architectures, most likely single CAN architectures, to multi-CAN E&D architectures. Even in multi-CAN E&D architectures, we are looking at multiple buses included. Like some part of the network would be CAN based, some part would be Ethernet based, especially for ADAS and related functionalities. Or autonomous is still on the same direction. Going forward, the architectures sort of are moving away from the domain-centric architecture to vehicle computer centric architectures. So vehicle computer architectures will be more of vehicle centralized architectures, and all the compute power of the vehicle will be in couple of devices, and they will act as the brain of the vehicle, and rest of the electronic control units will act as slaves. So there will not be much intelligence. They will act on the instructions from these vehicle computers. But they will bring a distinct advantage, the vehicle computers. They will be able to take far more decisions on the vehicle as compared to the current situation where the current technology does not support a lot of decision making. One example is the intrusion detection system that we intend to implement cannot decide on the vehicle whether a particular anomaly found on the END architecture or any of the buses is an attack or not, because there is limitation of computing power. You have to send it back to the cloud, all of this data, do the security analysis there, and then determine, okay, this vehicle is under attack or the vehicle fleet is under attack, and then determine remedies. On the contrary, the vehicle computer will support these kind of use cases. So that's one. I mean, I have two examples here, but one example I've already given. Another example is the limitations of the HSM technology. I'm just giving example. There are multiple. There are like tens of examples like this, but these ones are my favorites. The HSM technology, as on today, itself is cutting edge. So having electronic control units with hardware security modules, a separate core for doing cryptographic operations. This is a secure core for as a crypto accelerator. It is implemented by the silicon vendors. Multiple silicon vendors support this architecture, and then there is a firmware that will work on this secure core to give all of the crypto functionalities to the overall ECU. However, once we look at shifting from controllers to microprocessors and SoCs, the firmware are not in position to support these architectures as of now. The way they are developed is more driven from the controller base, and there is a long way to go. So then, plus there is no standardization. There is no the way HSM technology initially got a standard from Bosch, which was an open standard. Now, the HSM to be implemented in MUPI and SOCs is not really standardized. So, how to address this is one of the bigger challenges of future. But the current limitation itself is that the HSMs of today will not be in a position to deliver a vehicle computer sort of an architecture. The safety development of these kind of HSM solution is also quite tricky. So as long as functional safety requirements are met by developing these components as out of context safe, this will not work. And now you add the quantum preparedness for the HSM. HSM is very, very hardware dependent technology. So the hardware accelerators would need to support the quantum computing possibilities. So today's cases, we have controllers which are not quantum proof. They do not have quantum proof cryptography firmwares, and they are in field. And 5 years down the line, they may become very, very vulnerable because of quantum computing. So this is one of the biggest limitations that I see from HSM technology. And HSM is the nucleus of the entire security that we are going to implement in the software-defined vehicle. So welcome to the first challenge of limitations of the technology. Another one which I found interesting was the threats posed by EV charging infrastructure. I took this example. The first example is more from the heart of the security of individual ECUs. The other one is completely external to the vehicle. Now, vehicle OEM will take utmost precaution to ensure that the vehicle is secure. The onboard communication is secure, external communication is secure, everything is fine. But in the end, if we consider electric vehicles, they are going to be charged by EV chargers that are developed by multiple charging infrastructure players. These chargers will also be connected to the power sources in the backend. Over the period of time, with some sophistication, they might be communicating with the grid also. And when we look at the vehicle communication with the charger itself during the charging cycle, it is mostly currently by CAN or power line carrier communication, PLC. These kind of communication are already inherently insecure. Plus, there is no regulation on the charging infrastructure manufacturers in terms of what should be the security implementation and whose responsibility it is to ensure that the vehicle is not attacked. vulnerabilities of these inherently insecure protocols is not used and exploited against the vehicle which is currently charging. Now that is exploiting the vehicle's vulnerabilities. Now look at the infrastructure itself, the charger itself. The charger has diagnostics and other functionalities. Based on that, remotely from a server, you can switch on, switch off the charger. These are also based on pretty rudimentary kind of security implementations. So anybody could ensure that a complete line of chargers on a particular charging station are switched off by giving wrong diagnostic information. Simple attacks. So these kind of vulnerabilities need to be explored, and all of the inherently insecure elements need to be addressed on a very, very urgent basis. So now let's look at the third challenge, that's disruption at horizons that are very, very close than they seem. The first one is cloud technologies. A lot of cloud technology has emerged, and these cloud technologies can be used, leveraged to ensure that the vehicles are secured with respect to off-board attacks, or addressing zero-day vulnerabilities, or addressing remote monitoring capabilities, and so many others. So that ensuring that safe and secure vehicles are way beyond SOP. Some part of it is existing, but there is a lot that needs to be explored. The other one is impact of quantum cryptography on the current cryptographic algorithms. A lot of them are set to become obsolete. With quantum cryptography, one thing that needs to be ensured is the vehicles that are currently using existing cryptographic algorithms and being rolled out into the field have the capability to accommodate quantum proof algorithms in future. And second is ensuring that quantum proof algorithms are used on a wide scale in next 4 to 5 years. The third and interesting aspect is blockchain. So blockchain offers a lot of functionalities, of a lot of features. Most importantly, the decentralized storage of data, enhanced data security, reduction of manipulation. Now, these are going to be the aspect that the software-defined vehicle will need, because a lot of backend and the onboard data needs to be either used by the government agencies or the OEMs and tier ones. Depending on what is the nature of data, you can determine whether it can be a decentralized storage is needed, or there is a proprietary storage needed of this data, and ensuring security for future. So a good example is the onboard and offboard use cases, especially in interaction with smart city infrastructure, right? So this is where a decentralized system might be far more effective, and this needs to be explored. The long-term opportunities is more or less sort of pushing the limits, right? As you can see, there is a list of opportunities for OEMs, from shorter innovation cycles, saving a lot of cost related to quality. The software will be very scalable, and security will be enhanced. There is a great possibility with the SecDevOps development cycle to enhance the overall security of the SDV. What it means in immediate terms for long-term opportunities within cybersecurity ambit is the CSMS and the governance structure. So security culture will be created in the organization, just like QMS or the ISO audits that keep on happening so many times, right? So that's a quality culture. Similarly, cybersecurity culture will emerge, and the governance structure will ensure that the culture prevails in the organization. With a evaluation, continuous evaluation of disruptive technologies like AI, ML, blockchain, quantum computing, new ways of doing things better will emerge. So that's another opportunity to take a look at. Ensuring that cloud-based technologies support in vulnerability management or incident response as a service, proactive threat hunting. This is a very important aspect, because vulnerabilities published are there, but how do you ensure that proactively threats are being hunted, are being identified for your development, for your software defined vehicle? It will be very important. FOTA security, again, a lot of backend is involved here. And some of the external factors, so taking cognizance of inherently insecure factors that will impact the security, like grid is going to be insecure until the power grids decide to do something about it. They will be like that. So how to ensure that this out of control, out of context security is implemented? And last but not the least, ensuring that the limitations of today, like HSM I mentioned, or like the cryptographic algorithms which are already in field, how use of technology, the existing technology, little bit upgrade of technology, and a push of new technologies can ensure, with wise security investment and a residual risk calculation, ensure that the OEMs have a sustainable product in field. A quick summary is, cybersecurity in the holistic manner still prevails. Okay, it needs, for a little bit of tuning for the future for the SDV. And I mean, I have this is my favorite question. Have the rules changed? No. Defense in depth, you have to do. You have to minimize the impact. But your the paradigm needs to be, there has to be huge shift in the thought process, right? It's upside down. You have to ensure, you have to start looking from inside the nucleus of the vehicle security, like HSM, to the cloud-based technologies. There is a big plethora of technologies. There is so many handovers that the sensitive information is going to, and command control information is going to switch hands. You need to take a look at cognizance of all of these aspects, all of these interfaces, and start pushing in right tools, right methods to ensure individual security and minimize the impacts of future. And last but not the least, sustaining this reaction is the most important part. So if you have created a cybersecurity culture, if you have started delivering software-defined vehicle with the best of the security, ensure that the momentum is maintained, and this reaction of in the organization's DNA is sustained throughout the life of the vehicle and the OEM. So thank you very much.